All right, well, thank you, and thanks for the invitation, Jonathan. I'll be talking about how we create, diagnose, and control high-energy density matter on the National Mission Facility. Of course, this is a NIF, a very large facility. There are lots of collaborators, a gigantic team of people involved in doing all these experiments that I'll be talking about, and way too many to mention here, but just know that many institutions and many people contributed to all the results you'll see. So, technical difficulty here. I think usually when we start over, it will be okay. So, so it's an exciting time on NIF, and the way I see it is we're really setting a foundation for a very long future for the National Mission Facility. And it's a multi-decadal facility that can be used to do all sorts of exciting things in high energy density science. And so there are many exciting scientific results being obtained nearly every day on the facility. In FY16, this fiscal year, we talk about fiscal years and when you're running a big facility, we've significantly enhanced the shot rate, which allows a faster rate of learning by our users. And it's also enabled us to invest significantly more time in a program that I'm very dear to my heart, which we call the Discovery Science program on NIF. It's a program that allows us to use this incredible facility for academic work in partnership with universities to do this type of science they're interested in. We recently completed a new call for proposals for Discovery Science experiments. It's the first one we've done in more than 4 years, but now we're going to start doing it every year. The NIF stands for National Mission Facility, and so one of the big things going on NIF, the reason it was built and really set the specifications for NIF was to achieve inertial confinement fusion in the laboratory. I'll talk about that, where we are, where we're going, and what's going on. And we have some new capabilities coming online soon that will help us make more rapid progress. So I'll talk throughout my talk about high energy density matter. I just want to give you a quick intro to what high energy density matter is. It's matter, we define it somewhat arbitrarily as matter at pressures above a megabar, above 1 million times atmospheric pressure. So you can think of that as, you know, a pressure, but it's also an energy density. So as you'll see, we can use NIF to put a lot of energy in a very small volume in high energy density conditions. Just to reference you to some usual energy densities, some that you're used to, atmospheric pressure at sea level, but high explosives have an atmospheric pressure of about 1/10 of a megabar, 100 kilobars. The internal energy of a hydrogen atom, if you take 13.6 eV in the volume of a hydrogen atom, that's about a megabar in the sense of energy density. So if you start squeezing on it with that kind of pressure, it starts to change the behavior of that atom and the other atoms around it and squeeze on those electrons. The pressure at the center of the Earth is about 3.5 times 3.5 megabars. And if you go all the way to the center of the sun, you get to 250 gigabars. So very extreme pressures. And I'll show you that we can make pressures like that on NIF. So there are 3 major high energy density facilities in the United States. The Omega and Omega EP lasers at the University of Rochester, 30 kilojoule laser system. The Z-Pulse power facility where I used to work at Sandia National Laboratories in Albuquerque uses electrical energy to concentrate in small volumes to achieve high energy density conditions, and the National Mission Facility. And most of this HED science research is supported by the National Nuclear Security Administration. And the goal of the National Nuclear Security Administration is to maintain a safe, secure, and effective U.S. nuclear deterrent without further underground nuclear testing. And so that's who pays for most of the research I'll be talking about today, and paid for the building of the NIF. So NIF is the world's most energetic laser. It's a very large facility. I used to think of it as the biggest laser in the world, but a couple of weeks ago I got to visit the laser megajoule in France. It doesn't have a lot of laser energy in it. It's much smaller in terms of laser energy than NIF, but it's actually a much bigger building than the NIF building, more than 50% bigger. So I thought this was the biggest building like this in the world, but I was pleasantly surprised when I visited France a couple of weeks ago. And they'll be bringing up their energy over the next several years to make it comparable to the energy on NIF. So to put this facility in scale, you can see it's about the size of 3 football fields put together. You can change, of course, what the fields are depending on where you're giving the talk. It's different in Texas than it is here. So if you were to take the lid off the NIF building and look at it, you would see that there's 192 laser beams inside the NIF. And each of those beams at about 10 kilojoules is one of the biggest lasers in the world. And they can focus the 351 nanometer light that they generate to a very tiny volume. Basically, you can see there a target in the lower right-hand corner, about the size, a few centimeter across and a few millimeters in diameter. So all that energy goes into that tiny volume, and then we use it to actually go and create even more extreme conditions. So we can achieve matter temperatures greater than 10 to the 8th Kelvin, or about 10 kiloelectron volts, radiation temperatures, black body, you can think of Planckian radiation temperatures in the several hundred EV temperature range, 300 EV. We've achieved densities significantly greater than 100 grams per cc of hydrogen, several hundred times to several thousand times compressed matter, and pressures greater than 100 billion times atmospheric pressure. So there's a lot of very cool pictures of such a large facility, an amazing facility. I'll just quickly take you through a few of them. This is a picture of one of the laser bays. It has 96 beams in it. You can see some people here, so you can kind of get a sense of the scale of the facility. And actually, you only see 24 rows across, but there are 4 lasers deep. So each laser is about 40 centimeters by 40 centimeters at its full aperture. So very big lasers. Here's a picture of the target chamber where all that energy is concentrated and where we contain blast from the experiments. It's about 10 meters across, 10 meters in diameter. This is a picture that was created with Photoshop because there's actually floors in here, but you can see the lasers are configured to come in from the top of the facility and the bottom of the facility, and that's, as I'll show you later, to drive some drive. See many other ports around the facility, around the chamber, that are used for diagnostics and for loading targets and things like that. Here's a close-up of what we call the final optics assembly. This is where the light goes from infrared 1053 nanometers is converted into 351 nanometer light, and then is focused to the center of that chamber into that very tiny target. Amazing science and technology goes into having optics that can withstand the level of that fluence, that intense fluence of light, and actually only get damaged a little bit, and we replace a lot of optics after high energy shots and things like that, but kind of we have a whole factory of optics refurbishment to keep the facility running. And finally, the target chamber. The target is at the very center of it. It's just a little speck there. You can see some of the diagnostics we have configured, and this is a sophisticated system we use to align the targets. We want those targets to be aligned to about 50 nanometers, 50 microns, so the spots are on average are no more than 50 microns off from where they're supposed to be. So we have 192 different laser spots all arranged in a configuration to 50 microns in a centimeter scale target. And then, of course, the goal is not just to blow things up with all this laser energy. I mean, that's a cool thing to do, but that's not why we do it. We want to understand what's going on in this very short amount of time that energy is concentrated into such a small volume. So a typical NIF pulse is just a few nanoseconds long, kind of can be as long as 20 nanoseconds, but the peak power is only on for 2 or 3 nanoseconds. The peak laser power is 500 terawatts. To put that in perspective, the generating capacity of the U.S. is about electrical energy is about a terawatt. And so for a very short amount of time, the power, laser power flowing in NIF is 500 times that. And then we want to diagnose what's going on. So we have different experiment diagnostics. One is called Dante, to measure the temperature, right, of the inferno that is created inside NIF. Magnetic recoil spectrometer looks at the neutrons coming out of an implosion. The gamma reaction history looks at a DT 15 MeV gamma ray that happens with probability kind of 10 to the minus 5 for every DT fusion reaction that takes place. I'll talk a little bit more about that. And FLEX is a diagnostic that looks at hot electrons that are generated in this laser plasma interacting and can be very energetic, tens of keV up to 100 or 200 keV electrons. So we allocate, so we have this facility. It was constructed from 1997 to 2009. We turned it on in 2009, and since then we've been doing experiments, and we allocate the time to different programs on the facility. And we have different acronyms, apologize for those, but HED is high energy density science. This is things like material properties, understanding radiation transport, understanding opacity of materials. That's focused on what's needed to maintain that safe, secure, and effective deterrent. And you can see in FY14 there were kind of 82 experiments, and then the goal for FY15 here is about 130 experiments. So you can see we're going up in number of experiments we do. ICF, inertial compatible fusion, I'll talk a lot about that. That's our work trying to achieve fusion ignition in the laboratory. National security applications are applications outside of nuclear weapons that use and rely on high energy density physics. And then discovery science, and I'll talk a little bit more about that as well. And then we have a bunch of diagnostics on the facility. People want to make sure that those diagnostics are working right, so we use some facility time to check out our diagnostics and things like that. So as the shot rate has improved, we have been able to do more and more experiments, which means we can do more science. And that's really what this chart shows. We've been very focused on increasing the shot rate on NIF over the last couple of years. It's been kind of the #1 complaint from the users that there wasn't enough time to do the experiments that they need to do. And so, and it's a complicated facility, right? You have 192 laser beams, you have to align them, you have to get the targets in there, you have to get the diagnostics aligned, and it's still a relatively new facility, even though it's almost 5 years old now. And so learning how to do experiments more rapidly has been something we've been focused very much on in the facility over the last few months, and you can see that here. Here's the kind of quarters over the last, from beginning of last fiscal year, October 1, 2013 to October 1, 2015. You can see the number of experiments is going up. You can also see that the slices of time, particularly for the discovery science program, has gone up significantly. In fact, last year we did only 8 experiments for the discovery science program, and this year we're going to do 37 or 38, depending on how the year rattles out. So, and our goal for this year is to do 300 experiments. Our goal for next year is to do 400 experiments. And frankly, we don't know yet what goal we should set for the year after that. It depends on what the users want, what our sponsor wants. But doing more experiments is a way to learn more. And so, so I mentioned the academic use, the program we call Discovery Science. So we have, again, this multi-billion-dollar facility with a very large operating budget, and supported by the National Nuclear Security Administration. But it's a great tool for doing science. And so early on, it was recognized it'd be a shame not to spend some of the time on the facility doing science that's just really not driven by the weapons program, but driven by what's the highest quality science we can do, and what's the most interesting science to the outside world. And so in 2010, we awarded a bunch of time to 8 different teams to do discovery science. But unfortunately, in 2010, we had just turned on the facility, and we didn't really know, we weren't really experts at using the facility at that time, and we didn't have a lot of platforms, and we didn't have a lot of diagnostics. So we wanted that time, and we didn't actually give the scientists, these teams, a lot of time to actually do their experiments. Last year, for instance, I mentioned we did 8 experiments. Well, if you have 8 teams and you do 8 experiments, everyone's getting 1 experiment a year, which is a very slow rate to make progress. And so, as I said, now that the shot rate's gotten up and we're able to do more experiments, we've put significantly more time into this program, and we've actually agreed to kind of complete this first round of allocations, 5 years later. And now we're going to get into this mode of offering time every year to teams. Each team will get 3 days. 3 days can be used to do somewhere between 3 and 9 experiments, depending on how complicated they are. And they fall into a few categories. And the whole top row there is experiments that are trying to understand the behavior of material at high pressures, right? It behaves fundamentally differently than the material we're used to at everyday temperatures and pressures. It's compressible in ways that we don't really understand very well. We can use different codes to predict how material behaves upon compression, but we don't have perfect models for that. There are many different possible phases of material as you squeeze on a material like carbon, right? Graphite goes to diamond. You can, as you go up in pressure, you can even achieve other phases. Some materials, like lithium, have many, many phases as you squeeze on it. And so where those phase boundaries are, we don't know a priori, and so doing experiments is one way to understand that. And it's relevant not just because it's interesting science, what happens when you squeeze a material, it's a pretty basic question to ask, but also because we have a lot of planets we'd like to understand, and the details of the materials affect the dynamics of the planet. For instance, the details of our solid iron core and our liquid iron inside the Earth affects the magnetic field of the Earth. And similarly, if we look at exoplanets, and now, when we started all of this many years ago, there were very few planets, right? 8 or 9. Now there are thousands of planets that have been discovered. And understanding all those planets and understanding which of them might support life depends in part on the details of the materials that are involved in the construction, in those planets. For instance, do they have a magnetic field that can protect the surface from the solar wind in whatever solar system they're at? So that's a lot of what is going on in the material properties experiments. We also have experiments trying to study hydrodynamics, some just basic physics. How does the Rayleigh-Taylor instability evolve in the presence of radiation? Some trying to understand what we see out when we look out in the universe. And other things we try and understand, fundamental plasma physics of collisionless shocks that we see, again, when we look out with telescopes. So there are these 8 active projects that will be ending this year with collaborators, typically collaborators inside the laboratory who are close to the facility, who understand, are experts on doing the science with NIF, but working very closely with academic collaborators who have the drive and the desire to understand something that they can't achieve any other way but doing a NIF experiment. So we've had a number of teams that have been working over these last several years, and they'll be coming to a conclusion this year. So just to talk about a little bit of that, and this is something that Ray Janlo has been very involved in, along with other academic collaborators. So understanding the high pressure off-heat-on-neo equation of state of carbon and iron is being studied on NIF. So again, as I said, at the center of a planet, there could be a solid core, there could be, depending on the pressure and the density, depending on the material that the planet is made up of, it could be iron, like in a rocky planet like Earth, or it could be carbon. And so when you squeeze on carbon, what happens? How compressible is it? And so as we did those experiments back in, there's a publication from 2014. The experiments were done before that, I think in 2012, 2013. And there were many different models for how carbon might be as you increase the pressure. So a terapascal is about 1 terapascal is 10 megabars. So this is a kind of a peak pressure of 50 megabars. So this is carbon that's been squeezed up to 50 megabars. And you can see that it's not, we do work hard to squeeze the diamond in a way that doesn't create a lot of entropy. We try and squeeze it isentropically. That's much closer to what it will be like at the center of a planet. In a very short time, if you hit it very hard with a shock, then you get the responsive diamond on what's called the Hugoniot. But this experiment was done off Hugoniot to understand perfectly isentropic, we think. There are many possible reasons for that. As you squeeze on the diamond, you can introduce heat. You can do work on it in ways that we don't fully understand, so it doesn't agree with the cold curve. But it does put some constraints. It's likely that the isentropic diamond is below this blue line here. And this was featured prominently in Nature back in July of last year. Another problem that we're just starting to get engaged in on NIF, following on some work done on the smaller facility at the Omega Laser Facility at the University of Rochester, is studying astrophysical collisionless shocks. So I'll show you a picture on the next view graph, but if you look out in the universe, you can see clear blast wave shocks going out, and understanding the parameters of those shocks is just something that's interesting to astrophysicists. And we think that most of these shocks that we see, because the densities of matter involved are not high enough to create collisional shocks, they're collisionless shocks. So at very low densities, the question is, how do you form a shock wave if it's not through collisions? And we think that that's mediated through electromagnetic instabilities, like an instability called the Weibull instability. And so by using NIF to create a very hot, very fast-flowing plasma, we can run two hot, fast-flowing plasmas into one another. That will, in principle, generate the conditions like we see out in the universe, and we can understand how this electromagnetic instability, the Weibull instability, evolves and compare it to our calculations. So here's an example of one of those astrophysical shocks out in the universe. So here, the mean free path for particles in this supernova remnant is of order 40 light years. So if you think you need mean free paths to do a shock, and you look out and you see this has a very steep shock front, that's obviously much shorter than 40 light years, the mean free path. That means that something is creating that very sharp boundary, and it's likely to be electromagnetic effects in plasma physics, fundamental plasma physics. And so on NIF, we've used two foils that have been irradiated with lasers and have them, in a configuration where they're going to collide, and we can start to see the pileup of density there, which hints at a shock forming, a collisionless shock forming. We can also use nuclear diagnostics by choosing what materials we make these two different foils out of. We can understand the temperature and density of this plasma, and we're also working on ways of probing this plasma using proton radiography, using energetic protons to probe that are sensitive to electric and magnetic fields and look at how they get distorted as they propagate through this plasma. It is something we'll be working on in the coming year. And this also highlights one of the great things about these collisionless, all this Discovery Science work is the large collaborations that are brought together in order to do this kind of science, right? So it's a unique and rare opportunity to do work on NIF. There's not a lot of time devoted to all these different experiments, and so they grow large collaborations with people all around the world who want to be a part of this, who have something to add. And so that's fun, and it's great to have these people visit and participate in an experiment. So we recently concluded our FY16 Discovery Science proposal process. We had 42 proposals. We awarded 9 time. The committee that decided the priorities was chaired by Chris McKee from the UC Berkeley Physics Department. Unfortunately, Chris has now got a new job, and so he won't be able to be our chair for the next little while, but he did a great job and helped us a lot in making sure that the science we're doing is science that's valued not just by scientists at the lab, but also by scientists in academia. And we have a program leader, Bruce Remington, who gives a great talk on fundamental science and materials properties at high pressure. I encourage you to talk to him if you have any interest in this type of work. So the 9 new proposals that we're putting together, again, touch on these fundamental issues of material properties, of hydrodynamics at very extreme conditions. For the first time, we'll be doing some experiments in the area of nuclear physics. NIF can create plasmas and that are of interest to understanding fundamental nuclear reactions, the TT, triton-triton reaction, because we have enough energy and enough volume and enough, we can make it hot enough, we can get a significant number of those reactions to take place and understand how those reactions take place in a plasma. And we can also do these fundamental plasma physics measurements, one of which I just talked about, collisionless shock, but another one that's a lot of people are excited about is magnetogenesis. As we look out into the universe, we see magnetic fields that are much larger than we expect from just fundamental considerations. And so, but we have a lot of flowing plasmas out in the universe, and those flowing plasmas, as they interact with one another, can create turbulence and generate magnetic fields. And so we're going to use NIF to try and understand that process. All right, so now I'm going to shift gears a little bit and talk about inertial confinement fusion. And we'll try and give you a little intro of inertial confinement fusion. What is it, and what are we trying to do, where are we at, and where are we going? So, and inertial confinement fusion is a very simple idea. So we have 2 nuclei, a deuteron and a triton. If we send them together rapidly enough, we can create a fusion. We can overcome the Coulomb repulsion and have a fusion reaction take place. And when that fusion reaction takes place, it releases energy. And obviously, if we get enough of these, we can we only invest a tiny amount of energy in the deuteron and triton. We get a lot more energy out, and so we can get more energy out than we put in by fusing these atoms together. And we'd like to do this in a way that we get much more energy out than we put in. And there are 2 time scales that are of interest to this process. Suppose we have a blob of deuterium and tritium sitting there. It has a density, a radius, a temperature, and we can ask, how long does it take to fall apart? That's just a radius divided by a sound speed or a disassembly time. We can also ask, how long does it take for that nuclear process to take place and for the fusion reaction to burn, basically for plasma to react due to fusion. And that scales like a 1 over a density times a reactivity. So what we're really talking about in inertial confinement fusion is the competition between these 2 processes. We want the time for it to burn to be short compared to the time for it to disassemble. It's very hard to get to that limit, right? The easy limit is it falls apart much more rapidly than it burns. At very low temperatures, at very low densities and pressures, it will fall apart in a time scale short compared to the time for it to burn. But if we can get it hot enough, and if we can get enough density and enough radius product of that plasma, then we can actually get significant fractional burnup. And eventually, this formula breaks down, right? We can't burn up more than 100% of the deuterium and tritium there, but we can, so there's a correction to this formula, but we're still in the limit where this is always a small number right now, and we'd like to make it bigger. So to put some numbers to those conditions, typical rho times r, or density times radius product, you can think of it as the amount of stuff between me and the outside world. A rho r is 0.4 grams per centimeter squared, and a typical temperature is 5 kiloelectron volts, or 50 million degrees. Okay, so just knowing this, we can say, how hard or how easy is inertial confinement fusion going to be. So for hotspot ignition, I should have mentioned that those alpha particles, an alpha particle and a neutron come out in the DT reaction. The alpha particle is charged. It deposits its energy locally, so it can heat up more plasma and make it hotter and make the reaction run away. The neutron typically doesn't interact very strongly with matter, and so it just escapes and leaves quite rapidly. without depositing much energy. So if we want to do ignition, we want that alpha particle plasma to heat up and really to be dominated and burn up most of the fusion fuel there. We can estimate how much pressure we need, because the energy in the hot spot just scales like the mass times the temperature. It's just simple algebra, and basically it scales like something, the rho r cubed, the temperature cubed, but those are fixed in order to do significant burnup, and it scales like 1 over the pressure squared. So on NIF, I mentioned we had 1.8 megajoules of energy, but by the time we get all that energy concentrated at very high pressures into the deuterium and tritium fuel, we lose a lot of the energy. We only have about 1% of the energy left in that deuterium and tritium plasma at these very high temperatures and very high pressures. And so we only really have about 15 kilojoules we can use. And from that, we get a pressure that's of order 400 billion times atmospheric pressure. That's what pressures we need to get to in order for inertial confinement fusion to take place on NIF. And when we do that, we're going to be at very extreme conditions. We're going to have a small scale, a radius of order 30 microns, and densities of order 100 grams per cc. And it's only going to last for a very short amount of time, because this thing will fall apart in 30 picoseconds. But if it's hot enough and dense enough, we can get far more reactions in that time than energy we invested. We can get out many times, hundreds of times or thousands of times the amount of energy in the fusion fuel if we get it to light. And there's another approach to fusion which relies on doing things in steady state. It is much less, it doesn't rely on the very extreme conditions, but still requires very large magnetic fields to hold that plasma together. And those plasmas typically last for a few seconds and have pressures of a few times atmospheric pressure. So we're both doing fusion, but at very different extremes. So how do we get to 400 billion times atmospheric pressure? Well, unfortunately, we can't just turn on the 400 billion times atmospheric pressure, knob and use the laser to reach that condition. Even with the extremes that we're able to achieve on NIF, we're only able to generate pressures of order 100 million times atmospheric pressure. So we have to go from 100 million times atmospheric pressure to 400 billion times atmospheric pressure. We need a pressure multiplier of about a factor of 1,000. And the way we do that is we store up energy in a thin shell and implode it at very high velocities. So we basically think of a very thin shell of plasma that we're pushing on the outside. We're speeding up, speeding up, speeding up. Eventually it reaches the center, it stagnates, all that, and kinetic energy is turned into internal energy, into pressure, and that it generates the extreme conditions we need for inertial confinement fusion. And just some simple formulas for that. The pressure that we're at stagnation is related to the density we can reach to the 5/3 power, because it's nearly Fermi degenerate. We're imploding this at nearly Fermi degenerate conditions. And the specific energy scales like the velocity squared. It goes like alpha rho to the 2/3, and so we can say that the stagnation pressure scales like the velocity to the 5th power. So the faster we can throw this thing, the more likely we are to reach those conditions we need. But it also depends on how close to isentropic we can get it. We can either use indirect drive. We shine the lasers on a hohlraum, a cylinder that creates X-rays. Those X-rays bathe this capsule and then implode it. Or we can shine the lasers directly on a capsule and implode it like that. Either way, we don't get very large pressures, and we have to do a lot of pressure multiplication in order to achieve the extreme conditions. And what that drives us to is a very thin shell to store up all this energy. And thin shells, as you'll see, are subject to instabilities, and that's one of the challenges we have for inertial confinement fusion. So I mentioned instabilities. You have a light fluid pushing on a heavy fluid. The light fluid is radiation or the laser light. The capsule is made up of plastic. I'll show you an example of a capsule in just a second. And so you have light pushing heavy, it's unstable, and so instabilities grow up and can penetrate into the hot spot and perturb it. We also are trying to squeeze something that's from large scale down to small scale, because we're trying to compress it as well. We're trying to get that density up. And so if you don't squeeze uniformly, you can think of it as squeezing a basketball down to the size of a pea. So if you push a little too hard on one side, then you're not going to get a nice round pea at the end. You're going to get something that's distorted, and that won't get hot enough to fuse. And so, so there are many constraints on doing inertial confinement fusion in the laboratory. So here's the detailed configuration showing all the laser beams coming in. with a capsule on the inside. The capsule has structure. It's a plastic shell about 2 millimeters in diameter. It's in this case 2.2. It has it's made out of CH. It has some silicon dopant, and then on the inside we have a deuterium and tritium layer. We need to get that deuterium and tritium fuel in there, and we want it to be a perfectly spherical, because we're going to try and squeeze this up in 3 dimensions. And getting a DT ice, so the way we do that is we freeze it. And so here is an example of the cryostat inside NIF. The target is in there, the capsule's inside that. This is held at minus 290 degrees until just before we do the experiment. That shroud opens up in just a few seconds, and then the lasers fire in and drive that capsule in at velocities of hundreds of kilometers a second. So here's a detailed blow-up of the capsule. It's a very sophisticated little miniature hohlraum, we call it. It's a little oven. We keep the temperature, control it to about 1 millikelvin across the entire capsule so that we get the DT layer to be uniform. We have to control where all the light that comes in and doesn't hit the target goes off to, and so we have all these little ripples out here. It's really a work of art. It's beautiful, and it also costs about $200,000 to make one, and we blow it up every time. So it is an expensive proposition. So, so here is a plastic ignition capsule, 2 millimeters in diameter. We have to control the surface roughness on this capsule to better than of order kind of tens of nanometers roughness, so very, very uniform and very, very smooth. Here's what it looks like with a DT layer frozen on the inside, just a few tens of microns thick. And then here's a simulation of what this whole process looks like. You can see the laser beams coming in. We have 2 different cones of laser beams. The power is very carefully controlled in time to control how close to isentropic that implosion is going to take place, how close to Fermi degenerate the fuel is. And you can see we need to control the power and energy deposited in these plasmas in a very exquisite way in order to make sure we don't push too hard on this side or push too hard from here in order to get that implosion to come in nearly spherically symmetric. And of course, in the calculations, we're able to find ways of making that happen, but nature is more challenging, and we don't have the same control in nature, right? Understanding what's going on, it's easy to do in a code. It's a lot harder to do in reality when this whole thing is happening in the course of just a few billionths of a second. So here is a more, just looking at the capsule, looking at the instabilities growing up. This picture over here is zooming in, so it's kind of confusing. You're not looking at the same radius the whole time. Here is the example with looking at seeing the capsule shrink as a function of time, but you can see those instabilities growing up, getting very big late in time, and perturbing that hot spot, that hot DT plasma that we want in there. That's going to be the core of the fuel that we want to light and ignite. And you'll see as I go through that instabilities are one of the things that were something as we control them, we were able to make more progress, but we still have a ways to go. So, in order to understand and diagnose this plasma and its evolution, we need a lot of different tools. We need a lot of different experimental platforms. We need a lot of different measurement techniques. We want to understand this hohlraum environment, the radiation environment that we're creating. We want to understand how much laser light that we are trying to put in is actually coming back out and scattering. The plasma can turn into a mirror and reflect the light back out, and we have to control that and understand it, which in turn can affect the symmetry of this implosion. We want to understand the temperature and density conditions in this plasma because that controls where that laser light is deposited and where it heats up and where it turns into X-rays. We need to understand how the shocks that we are launching into this system are timed. We have to control them very carefully to kind of 50 picoseconds in order to avoid raising the entropy of this fuel beyond the Fermi degenerate limit. We want to understand how instabilities grow. We want to know how fast this thing is imploding. And we want to know what X-rays it's emitting at stagnation. So these are all tremendously challenging measurements. We're talking about measurements on the scale of tens of microns timescales of order tens of picoseconds. I'll show you some measurements, temperatures and X-ray energies of many keV. So it is a real tour de force experimentally. So we did some initial experiments back in the 2009 to 2012 era. We called that the National Ignition Campaign. It was a very dedicated, focused effort to try and bring up the laser, but also achieve ignition at the same time. And it was ambitious, frankly, too ambitious. And we ran into problems. So the initial experiments are shown down here in kind of parameters that matter, the fuel rho R and how much yield came out. And as you can see, right, if we were able to get ignition, we would get as much energy out and more energy out than we have in the laser that we use to drive it. So 1.8 megajoules, and the peak yields on NIF were about a kilojoule, a little more than maybe a few kilojoules at the end of 2012. And I'll talk about what we did and where we went to, and now we've made progress. We still have a ways to go. Okay, so one of the knobs we have on these implosions and the stability of the implosion is what we call the foot of the pulse. And that's kind of how strong the first shock going through that fuel is. If we hit it very strong, then it's not going to be very close to Fermi degenerate. It's not going to be as compressible, but it will also, the shell will be thicker and will be less susceptible to Rayleigh-Taylor instabilities. And so at the end of the National Ignition Campaign, a team led by Omar Hurricane and collaborators said, okay, let's hit the fuel harder. We're going to give up compression. We know we won't probably won't be able to reach ignition with a pulse like this, but maybe we'll mitigate those instabilities and control them in a much, and get much closer to what we predict should be taking place. And so we increased this parameter we call the adiabat. We thickened up the shell, so it became a less thin shell from a kind of aspect ratio of 20 to an aspect ratio of 10, and we lowered the convergence, how far it had to converge before it stagnated. And in calculations in advance, we took a shell that looks like this. You can see very perturbed from all those very smooth surfaces, but still growing by factors of 1,000 or several thousand and ripping up the shell, and made it much less perturbed, much more uniform. And we also did a bunch of experiments to confirm that. So there are many different wavelengths of modes that we worry about. There's a whole spectrum of modes. They can be decomposed into Legendre modes because it's a sphere. And so we could put on ripples on a capsule with various wavelengths corresponding to different mode numbers. And then we could implode it in an X-ray environment like the capsule would see. And we use some other beams, because we have 192 beams, to create an X-ray pulse and to image onto a detector, which isn't shown here, the growth of those ripples as a function of time. And so this is what you see, a series of pictures of the growth of the ripples as a function of time. You can see the predictions of how much it should grow, and you can actually see these dots, the experimental measurements, and the difference between this high foot configuration and the low foot configuration you can see is about a factor of 3 or 4 in the growth of those perturbations. So, so we knew by doing this high foot we would reduce those perturbations, and we measured it experimentally. Another thing we didn't anticipate at the beginning on NIF, but in retrospect is something we could have paid more attention to, is we have to hold this capsule in there somehow. And the configuration we use currently is what we call a tent. So the capsule is sitting, and it's a very thin tent. It's 100 nanometers in thickness. So a typical piece of paper is 100 microns, so 1,000 times thinner than that typical piece of paper. But it's still 100 nanometers. And that perturbation and the details of how that tent wrapped around the capsule led to, here's an X-ray radiograph. It looks like a baseball, but it's actually our capsule imploding, and it should be perfectly round. But you can see it's got a big stripe in it where this perturbation from the tent has ripped into the capsule and is distorted and ruined the fuel on the inside and caused a very poor performance of the capsule when it stagnates, because there's a lot of now plastic in there that radiates a lot and doesn't like to fuse. So when we did this high foot pulse, again, we saw much less perturbation from the tent material. So you see a much smoother capsule, much more spherical capsule. It's still being perturbed by this tent. We'd like to make the tent smaller. In fact, we've now gone down to 30 nanometer tents, but they're still perturbing the capsule. So we'd like to find a better way of holding the capsule in there so that it isn't perturbed by the structure that's holding it. But when we put all these things together with this high foot configuration, we were able to get much higher performance of yield. We knew we were giving up on the fuel rho R because the entropy was too high. It wasn't as compressible, but we were able to get yields much higher in the now up to 27 kilojoules is the highest we've done to date. And so that's a big step forward, but we still have a factor of about 50 to go in order to get to ignition. One of the exciting things about this plasma is something that has been a challenge for fusion for a very long time, is to create a plasma which generates more energy than was just invested in the fuel. That's not enough to make energy, to put energy on the grid, but it is a benchmark, a threshold that hadn't been crossed previously in laboratory fusion research. And so on these high foot shots, in particular a few of the highest yield shots, we generated more energy than we invested in the fusion fuel through this implosion. And so that's the first time that that's been done. It's not a place to stop. We still have a long way to go, but it is an exciting thing, and it gives the team hope and ideas about the future directions. So to summarize where we are and what kind of configuration we've created, we've generated 27 kilojoules of fusion yield. We've reached densities in the shell of about 500 grams per cc. In this hot spot, the hot core that isn't as dense but very hot, we've generated conditions about 40 grams per cc and 5 keV. Peak pressures about 200 billion times atmospheric pressure, and a rho R of about 0.75 grams per centimeter squared. In each of these metrics, we're about a factor of 2 off from what we need to do for ignition. And so together, the yield scales strongly with each of those. And so the yield we're off about a factor of 50 or so in the yield. So we have a ways to go. And we're looking at many different options to go forward. So there are many different capsule materials we can use. We focused on plastic to date, but it turns out that diamond is also a promising material to make the capsule out of. A beryllium is a material we've recently done some experiments on. Each of those changes that hohlraum environment, changes the pulse shaping requirements, changes how much energy we can deposit into the fusion fuel. So we're exploring those over this kind of FY15 and FY16. We're also looking for hohlraums that are much less dynamical than, much less, the laser has much less material it has to propagate through in order to couple its energy into the hohlraum and into the capsule. So the original hohlraums were filled with lots of gas. The laser energy gets absorbed and refracted and reflected in that gas. That changes and makes it challenging to control the symmetry of that implosion. Recently, we've done experiments with much less gas in there, and it's much easier to get the energy to deposit. Nearly all the energy gets deposited in there, but then this hohlraum wall starts to move significantly, and that changes the symmetry on the implosion. And so that's what we're working on right now. So we want to move from, to increase efficiency and have more predictability in our implosions. But that's not all we're doing. So there's a lot we can control with the design of the target and the hohlraum configuration. But we also want to try and understand and diagnose better what's going on in this very hot, tiny little plasma for just a few tens that exist for just maybe 100 picoseconds. And so we've been limited by our cameras. Our cameras are very fast, 100 picosecond camera, but 100 picoseconds is long compared to the time scale of the implosions that we're interested in. And so, in fact, we recently developed a new dilation imaging system which takes the X-rays pulse and spreads it out in time and then collects it on a camera that can resolve, kind of at the tens of picosecond time scale. So we can actually, basically have you can think of it as a time scale we can control on when the X-rays get to our detector and when we're actually measuring them. So we can study things on the 10 picosecond time scale. So here is a picture on a 10 picosecond time scale. At 100 picoseconds, this would all look like one blob. And so that's starting to give us insight into how that plasma is flowing, how it's getting hot inside that hot spot. We have a number of other diagnostics that are being invested in to try and better understand with time-resolved neutron and gamma ray spectroscopy, 3D neutron and gamma ray imaging, high-resolution X-ray spectroscopy. Basically, we need better measurements because the measurements we have don't tell us exactly what's going wrong. Why is the implosion not behaving more like the simulations? And so by better diagnosing it, we'll be able to get some clues on where to go next. What do we have to control better? Maybe this spec we have on how symmetric the laser has to be or how uniform the pulse has to be from the various different lasers all coming together, or the time control over the shock timing. You know, there are many things that we can control, but we need some clues on what to do next. And diagnostics will help us with that. We're bringing online a new capability to do advanced, we call it the Advanced Radiographic Capability. There are many lasers around the world that have very high powers, right? I mentioned NIF's power is 500 terawatts. It's the only megajoule laser in the world, but if you shrink the time scale over which the energy is delivered, you can get to very high powers without a lot of energy. And those types of lasers are very good at creating very energetic X-rays, and those energetic X-rays are very good at taking pictures of things that we can't do today on NIF. And so we have this advanced radiographic capability. It will have 4 different beamlets. It will be able to shrink, get almost the same amount of energy as in a NIF beamline, so not quite 10 kilojoules, but a kilojoule, but deliver it in something like 1,000 times faster. And so that will allow us to take better images of imploding capsules, to study things like strength of materials, but kind of most importantly for the ICF application, take an image of where that cold fuel is just as the capsule is stagnating in that 10 picosecond time, tens of picosecond time frame. Where is the hot part? Where is the cold stuff around it that's supposed to provide the confinement? We don't have a picture of that today, and that's going to be developed over the next year. And so with that, I'll end with where I started. It's an exciting time. We're having a lot of fun. There's a lot of room for collaboration with universities. I'd be delighted if anyone wants to come out for a tour. I'll be happy to set it up, and I'll take any questions.
That you're achieving fusion reactions, but you're not, it's not a runway, so it's not ignition. Is that the right?
That's right, yeah. So it's starting even to start the self-heat, okay? So there's more, if we didn't have, if the alpha particles didn't deposit locally, the yield from the best performing experiment would be of order 10 kilojoules. I rushed over that, but instead, because the alpha particles deposit their heat, that 3.5 MeV gets deposited into DT and heats it up even more, making more fusion reactions take place. We actually kind of get twice the yield that we, than we would have. Of course, eventually the goal is, to get yields that are many, many times the yield, the energy we've invested in the fusion fuel. So we're kind of doubling it right now, but we would like to, get many times that. So that's what's happened for the first time in the last year. Let's see. So in order to control the instabilities, we'd like to make it denser, but we have to control these instabilities that are ripping apart the capsule. And the way to do that, one way of doing it, may not be the only way, but the easiest way is to only change, all we did was change the pulse shape of the laser entering into the hohlraum by increasing this area here we call the foot, the early part of the pulse. And so by doing just that change, we went from something that looks like this to something that looks like that and got this much better performance. There may be other ways of doing it, but this was the easiest way to do on the shortest time scale.
Why does it take nanoseconds to this capsule?
Huh?
Why does it take nanoseconds to this capsule until you see the power increase?
So, so the history of the laser power versus time. So at low pressures at the beginning of the pulse, we want to put a shock that's of order a megabar into this fusion fuel. And it takes a long time for that shock to propagate through that shell thickness, a long time meaning many nanoseconds. So we keep the power low. If we turn the power up to full blast right away, we would ruin the entropy, ruin the adiabat of the fuel, and it would be very, very incompressible, and we wouldn't get very good performance at all. So we carefully control the time of the shocks that propagate. There are multiple shocks. Here's the first shock, second shock, third shock, a fourth shock actually in this configuration. In this configuration, there are only 3 shocks, and we want those shocks to go through one at a time through the fusion fuel. That controls it keeps it as close to isentropic, as close to Fermi degenerate as possible.
So what are the constraints for scientists who want to blow stuff up? What are the constraints on the capsule and the laser profile? And are there standard sets of instruments for measuring response, or do people propose
So we have a set of, so that we can dial in the laser pulse shape. There are some laser pulse shapes that are particularly damaging to lasers, so we're not going to let users, blow up the laser. You can blow up whatever you want in the target chamber, but not the laser itself, because we want to use it for the next shot. But so you can see we can control the pulse shape in kind of great detail, exquisite detail. We have a number of diagnostics, kind of 50 diagnostics. We're putting new ones on all the time. It is no small endeavor to put a new diagnostic on NIF, because it's something that we're going to want to use repeatedly. It's going to have a control system. So we do have collaborators from outside come and build diagnostics, but it's not something you can think of doing in a week, or it's probably a couple year effort to put a new diagnostic on NIF, and to make sure it's integrated into the system. It probably costs fractions $1 million or something like that, right? Depending on the complexity of the diagnostic. So, but there are, there's a big effort right now going on to try and put brand new diagnostics on NIF from a national collaboration of kind of all the institutions working on it. So there's a good time, they're looking for ideas of what measurements to make right now. So the materials in there, in general, what we don't want is a lot of mass in the target, because we have optics, 192 different laser beams coming in through big optics. So if there's a lot of mass, it could blow out and blow up one of the, hit one of those optics. It will create a little. So as long as the target vaporizes, and we do hazardous materials. We've done beryllium, we've done plutonium. So generally speaking, we can do a lot of different materials. There may be things that that outgas or something like that, but there's a wide variety of materials you can bring in. Yeah.
So for the past year, you had on average one shot every 2 days. How short can you have pulses?
So so we've done as many as 3 experiments in a day. We'll, this year we'll test out a capability to do kind of 5 to 8 experiments in a day. The fundamental limitation is that the amplifiers that power the laser heat up the laser glass, and that until it cools down, the laser beam would be distorted as it propagates through that laser glass, and that's of order 4 to 8 hours before it cools down. So experiments where we're going to do multiple ones in a day, we'll use not all 192 beams. They'll use some subset of the beams, and then we'll use another subset, and we can, because we still have a lot of energy, right? A lot of experiments can be done with 100 kilojoules, and there's a lot of ways to get 100 kilojoules out of all 192 beams.
If you go back a decade or two, the laser itself is much smaller. People thought you could do fusion with it. But could you say what you think might happen in the next decade or 10 years from now? Are you just going to be doing more experiments with this, or is there something very different?
So that we're working on that right now. What is the next thing? Right? We did this amazing thing, put this facility together. I see that for the next few years, The challenge will be, taking this facility we've got and learning from it. So that's hence the emphasis on diagnostics. And we can put more energy in, not a lot more energy in with NIF in the current configuration, but maybe another 50% or something like that by optimizing, tweaking. So that's the focus for our kind of the next few years, right? We would love to get ignition. If we don't get ignition, we'll be looking for what are the things we need to do to get ignition. We could change the configuration of the laser and make it a symmetric configuration where the beams don't come in from top and bottom, but they come in all the way around. People have ideas about pulse power. It may be a pulse power facility that can do that. The long-term goal for this inertial confinement fusion program is to do high yield, to make hundreds of megajoules of fusion yield. And then you can use that hundreds of megajoules of fusion yield to do all sorts of very interesting experiments. But that's probably and then the very, very long-term goal is if you wanted to do that a few times a second, you could, think about how to put energy on the grid. But that's way down the road. So.
Okay. So you get about 2 times as much energy out as you put in, and that's not yet ignition. So how much do you need to get out before you have ignition?
So again, it's the energy into the fusion fuel. Okay, so we put 1.8 megajoules into this can. Okay, of that, 150 kilojoules is absorbed by this capsule. Okay, because a lot of it goes out this way, or goes into the walls, or just doesn't hit the capsule. Of that 150 kilojoules, 10% ends up into the DT fuel. Only 15 kilojoules ends up into the DT fuel. And so we got 27 kilojoules out. And as you can see from this picture here, we believe at some point there's a line, according to our calculations, there's a line where once you get across it, the fusion reaction runs away and takes off. And we have calculations that say where that is. It's not very far from where we are. In another metric, it's about this kind of factor of 2. But is that right? We don't know. So exactly how far we are away, we don't know, and we'll hopefully find out someday. That's the goal. So.
So as far as direct versus indirect, how are you still pursuing direct approaches versus the hohlraum?
So direct drive is the mainline approach at the University of Rochester Laboratory for Laser Energetics. They have a 60 beam, 30 kilojoule laser, and they have it configured so they can shine all the lasers directly on the capsule. The advantage is it's much more efficient, right? It doesn't lose all this energy going into the hohlraum. It can couple many times the energy to the capsule and to the fusion fuel. The disadvantage is that laser is not perfectly smooth. It has little imperfections on it, and it can create fingers and instabilities that grow up even more virulently than the ones that we see on the indirect drive configuration. And so the advantage is more energy, more coupling. The disadvantage is more instabilities. And over time, we're going to try and figure out, which one wins, basically.
Okay, question back there, and then one more for this one. No, I was just wondering, the cost of energy that you're creating, a kilojoule is a kilowatt times a second. Kilowatt hour costs 10 cents.
That's right. So
It costs you $200,000 to make it.
exactly right. So if you were going to make a target like this every time, there's no way it would ever make economical sense to try and even conceive of energy on the grid. And you can't, so again, it's a long way away. You have to figure out how to do it once. That's definitely the first step, right? You have to get more energy out than you put in. And you have to figure out, can you do it at high rep rate? You have to do it in order to make a, economical gigawatt power plant. You'd have to do it at, several hertz. Again, we shoot once or twice a day, so we're a long way from that. And the target costs about 25 cents. So there's no shortage of challenges from here to there, right? And I'm definitely not saying we're ready to do any kind of energy program. But someday, decades from now, right, it could be something that people think about.
Okay, now the second speaker again.